Right, electric fields. We're talking about stationary charges. Once the charges start moving, then we'll be talking about magnetic fields. And that's the realization that James Clerk Maxwell had when he realized that electric fields and magnetic fields are just two sides of the same coin. I'm sure you know this already, but like charges repel, unlike charges attract. So two positives, they're going to force each other apart. Two negatives, similar story. But what can I say? Opposites attract. Charged particles can be charges. And yes, like we were saying about gravitational objects with mass, we can treat them as point charges. We're rarely actually interested in their physical dimensions. We just treat them as points without volume. Like gravity, they can be represented by field lines. It's a non-contact force, therefore it can be represented using the language of fields. The only slightly tricky thing to remember is that because electric fields can be repulsive as well as attractive, whereas gravity could only be attractive, you just need to remember to get the direction of the field lines correct. And they are defined with reference to a small positive test charge. So the field lines flow the direction that if I put a tiny positive test charge in there, small enough that it doesn't create its own significant field and distort the field we're interested in studying, what direction would that positive test charge move? Well, it would move out in this picture because positive charges repel each other. If I put it here, it would move in because opposites attract. If I put it in this picture, if I placed it here, it would simultaneously be repelled by the positive charge and attracted by the negative charge, and so it would flow along that arc as drawn. And if I put it in this field here, it would follow this trajectory. It's as simple as that. You can see then that not only is there this fun interaction between particles themselves, but you can see the fields also are affected by other fields. Field lines don't like to converge generally, unless they're from opposite sources, unless they flow naturally one into the other, as here. Whereas these field lines, it just looks to the eye as if they are trying to avoid each other. Electric field lines. Point charges, a bit like in gravity, they're radial fields. You get uniform fields if you've got charged plates, so two sides of a capacitor, perhaps. What if you combine the two? Well, it's this hybrid picture where you have what would be a radial structure, a radial field, but it ends up sort of being slightly distorted by the fact that the field lines will all converge on this uniform surface if you go far away enough. Okay. Generally, when we study charged plates, we'll always be focusing in the bit in the middle where the field is uniform. But for those interested, at the edges of our plates, the field does start to become non-uniform and split out into these sort of round shapes instead. That's why, yeah, so you've got non-uniform edges. And so that's why we tend to study plates, charged plates, where the plates are very close together, so such that the scale of their separation is way smaller than the scale of their width. This side it's radial,